See, in the last class we looked at all the concepts and questions related to the circular orbits of the satellites. So here in this class we'll look at the other possibilities, especially the elliptical orbit. But in the meanwhile, our Tintu wants to perform some experiment. He wants to get the ball moving in a circular orbit around the planet. Let's see if he gets the speed right. See, he got the speed right, so mission success. But he ended up in a mishap.
Can it really happen?
See, this is kind of a comical depiction just to get the point across. Don't take it seriously. So this can't happen in real life situations. See, first of all, no human being is capable of throwing an object at a speed close to 8 km per second, which is the orbital speed near the surface of the Earth. Even if one manages to do so, when you're too close to the surface of the Earth, the atmosphere is so dense that it won't let the object continue moving with the same speed. Ultimately, the object will slow down and crash onto the surface. So our Tintu is very safe. Don't worry. At the most, he can do something like this. See, we need to get to an altitude where the atmosphere is thinner. From there, if an object is projected at a speed exactly equal to the orbital speed, this object will move in a circular orbit around the planet. And it is this circular orbit that we talked about in detail in the last class, and now it is time we moved on to the next concept. Alright, so before we get into the elliptical orbit and other stuff, let me run through some important points related to the circular orbit that may be required for solving questions of this topic too. So do you remember all the formulae related to the circular orbit? So the first and foremost, so that is the orbital velocity. So that is the speed at which a satellite is revolving around the planet Earth in a circular orbit. So the orbital velocity, denoted by VO, has the formula the square root of gm divided by r. So this speed is independent of the mass of the satellite, and this capital M here denotes the mass of the planet Earth, or generally mass of the parent object about which the other object is revolving. Now if you consider a planet revolving around the sun, so this M here denotes the mass of the sun, and r here is the orbital radius, which is the distance of the satellite from the center of the Earth. And similarly we have this escape velocity, and escape velocity, so that is the minimum speed required for an object to escape from the gravitational influence of the planet. So that has the formula the square root of 2gm divided by r. So just like the orbital speed, so even this one is independent of the mass of the object, and also this is independent of the direction of the velocity. So in any direction you throw an object at this speed, it will escape from the planet. Don't drop it vertically downwards though. If it hits the surface, it is not going to escape from the planet. And so this speed can also be written in terms of the orbital speed. So this is root 2 times the orbital speed. That means the escape velocity is little more than the orbital speed. So this is approximately 1.41, which means 41% more. So that means if you increase the speed of a satellite by about 41% or so, it will escape from the planet. So that is escape velocity. Okay. Similarly, so the next one is the orbital period. That is the time taken by the satellite to complete one circle around the planet. So that has this formula. So the square of the orbital period, so t squared, is proportional to the cube of the orbital radius. So this relation is there, and also we've written one more formula if you remember. So the time period, so that is equal to 2 pi divided by root gm multiplied by r to the power 3 by 2. So we can use this formula to find the orbital period of a satellite or any rotating body. And the next one is the energy of a satellite. So what is the energy of the satellite? So the potential energy. See, the satellite is at a distance r from the center of the Earth. So that means the potential energy is given by, so minus gmm divided by r. So this is the potential energy of the satellite, and this is a constant value. At any point on the orbit, this value is constant, as this r is the orbital radius, which is a fixed value. So potential energy at any point on the orbit is a constant value. So just like the kinetic energy, so kinetic energy is half mv square. So v here is the orbital speed, so which is again a constant. So kinetic energy is also constant at any point on the orbit. So if you want, you can substitute this value of orbital velocity from this expression and add these two values. So we get the total energy. So that is that has the formula minus gmm divided by 2. So this is the total energy. So all these values are constants for a circular orbit. So these are some important points related to the circular orbit that we can refer to later when we want to solve questions of this topic too. So here is the list of concepts that we are going to look at in this topic. So the first one is about various trajectories of a projectile. See, so far we have done only the circular orbit. Now here we look at the other possibilities. So the next one is about ellipse. So as this topic is about the elliptical orbit, it's important that you have some basic idea about this ellipse before we proceed with the next concept. See, this is purely a math stuff. If you had already done this in your math course, so we wouldn't need to do this here. But anyway, I'll mention a few quick points about this here. And the next one is about the angular momentum and energy. So this is not specific to this topic. So you've done this already in various places. But as there are many questions based on this concept, I'll mention some points about this here. And the last one is about the Kepler's laws. And that's what this topic is all about. And so these are the things we'll be looking at one by one, and once we are done with all these concepts, and we will solve questions based on these ideas. Alright, so here we look at the various trajectories of a projectile. So the first case is the obvious one. So when the speed of projection is exactly equal to the orbital speed, so this object will move in a circular orbit around the planet. So we are pretty familiar with this case, so we'll move on to the next one. So when the speed of projection is less than the orbital speed, this time the shape of the path is called an ellipse. So it will move in an elliptical orbit. It gets little closer to the planet. Okay, so this shape is what we call by the name ellipse. Yes, Minto, what's your doubt?
What if it falls on the surface?
See, when the speed of projection is less than the orbital speed, it will always take an elliptical path. If it hits the surface, the path gets truncated. So if you complete that curve, it will be an ellipse.
But we've learned that the path of a projectile is a parabola.
Considering this path to be a parabola, we have done a whole chapter called projectile motion. And what about that? That's what you're asking, right? Alright, so let's consider this example. See, our Chintu is throwing the ball. This path is supposed to be a parabolic path, right? But to conclude that it's a parabola, so we have done a lot of assumptions. First of all, we assume that Earth is flat. So the gravitation force is acting in the vertically downward direction. So the direction of gravitation force is fixed, vertically downward direction. But in reality, Earth is not a flat surface like this. So it is curved. So that means at different points, the gravitational force will act in different directions. At different points, it will be pointed towards the center of the Earth. So that means it is not in fixed direction. So that makes the path deviate from the original parabolic path, and it takes more of an elliptical shape. So the parabolic path that we had assumed was an approximation when it comes to objects which are very close to the surface of the Earth, and the speed of projection is very less compared to the orbital speed. But in a larger perspective, it is an elliptical orbit. Do you understand? When the speed of projection is less than the orbital speed, the shape of the path is elliptical. Alright, so now we will take the next case. Alright, so the next one is when the speed of projection is more than the orbital speed but less than the escape velocity. In that case also, it will take an elliptical orbit. So here it tends to move away from the planet, right? But it will come back to the same position anyway. So here it takes an elliptical orbit. Alright, so the next case is when the speed of projection is equal to the escape velocity. Then in that case the object will no more orbit the planet, it will tend to move away from the planet. Alright, so it will escape from the gravitational influence. But it is here that the shape of the path is a parabola. Alright, so here it moves away from the planet in a parabolic path. So that means when the speed of projection is equal to the escape velocity, so that is when the object moves in a parabolic path away from the planet. Alright, yes, so the next one is when the speed of projection is more than the escape velocity. Obviously even here this object will move away from the planet. Okay, it will escape from the planet influence. Now this time it takes the shape of a hyperbola. Alright, so this object will move in a hyperbolic path, so we don't need to know what a hyperbola is. So our main focus is on the elliptical orbit. That's what we are going to look at mostly in this topic. Alright, so these are the different trajectories of a projectile. Alright, so let's look at one by one. If you consider all at once, it's kind of difficult to observe, so let's take it one by one. So the first case is when the speed is less than the orbital speed. In that case, it will be an elliptical orbit. So the next case, when the speed is equal to the orbital speed, then it will take a circular orbit. So next, when the speed is little more than the orbital velocity, even here it will take an elliptical orbit. So the next one, when the speed is equal to the escape velocity, so it will move away from the planet in a parabolic path. The next one is when the speed is more than the escape velocity, so even here it will move away from the planet but in a hyperbolic path. So these are the various cases. All you got to note down is just this figure. Alright, as this topic is more about the elliptical orbits, so we need to have a basic understanding of this shape called ellipse. See, we're not doing this in detail here. It will become a math course in that case. We'll just mention few points which are relevant to our discussion. What is meant by an ellipse? See, take this circle, you squeeze this circle, so the shape gets distorted and it will be like an elongated circle. So this is what we call by the name ellipse. So if you observe, in the process of the circle becoming an ellipse, the center gets split into 2 points, each of which is called by the name focus. So there are 2 of them, so we call them foci. You can say foci in the Yankee style. Alright, now see, take this circle. The circle has the property that any point on the circle is at a constant distance from the center. CP distance is always constant, called the radius of the circle. Now similarly, in ellipse, take a point P on the ellipse. So this point P, the sum of the distances from the 2 foci is always constant. So S1P plus S2P is always a constant value wherever the point P moves. So this is one property of this ellipse which is not very relevant to us, but still there are a few more points about this ellipse that you should be familiar with, like, see, the longest chord of this ellipse is called by the name major axis, whose length is taken as 2a, and half of the length a is called the semi-major axis. Similarly, the perpendicular chord through the center, that is called minor axis, whose length is taken as 2b, and half of the length b is called the semi-minor axis. And now, particularly, if a and b are equal, so this ellipse will become a circle. So circle can be considered a particular case of ellipse with the a and b equal. If you make the length of major axis and minor axis equal, so this ellipse will be a circle only. So circle is a particular case of an ellipse. So there are a few more terms which you should be familiar with, like an eccentricity of an ellipse. The eccentricity E is given by the formula, so square root of 1 minus b squared divided by a square. So this formula can be used to calculate the eccentricity of an ellipse.
What is the significance of this eccentricity?
This eccentricity gives you an idea of how close this ellipse is to the circular shape. Eccentricity lies between 0 and 1. See, the closer the value of eccentricity to 0, and it will look more like a circle. And if eccentricity tends to 1, it will be like a flattened ellipse, more like a straight line. So eccentricity lies between 0 and 1 in a way that defines the shape of this ellipse. Okay? And the distance from either focus from the center is calculated by the formula AE. Okay, just remember this as a formula. That means what is the total distance S1P? P is one end of the major axis. So S1P is from the focus to the center, the distance is AE, and from the center to the end point, that is the semi-major axis, which is A. So the total distance S1P is A plus AE. Similarly, S1Q is A minus AE. So these values are required later on. So we'll talk about this in detail a little later. And just one last point about this ellipse, that is area of ellipse. So we know area of circle pi r square. Similarly, area of ellipse is calculated by the formula pi AB. So pi AB is the area of the ellipse. So as a particular case, if A and B are equal, so it will become a circle, pi A square. So that is the area of the circle, right? So remember this formula for area of ellipse, which is pi AB. So these are some important points related to the ellipse. So all those points which we talked about in ellipse are summarized here in this figure. Alright, so next we'll talk a little bit about the conservation of angular momentum. So this concept is nothing new to you, so we've already done this, but because we are going to use this concept in many questions here, and I'll mention a few points about it. So the concept of the conservation of angular momentum. So what is an angular momentum? See, when an object is revolving around another object in an elliptical orbit at a distance r from it, so with the speed v, so the only force acting on this object is the gravitational force due to this object. So the gravitational force is acting in this direction. So the gravitational force is in line with the radius vector. So we know that the torque, right, is calculated by the vector product of the radius vector and the force vector. But the force here is parallel to the radius vector, so the total torque is 0. So when the torque is 0, the angular momentum is conserved. So at any point on the orbit, the angular momentum is a constant value, and that is the concept we are going to use here. So the angular momentum L is a constant value at any point on the orbit. So that is the idea which is important for solving many questions. So first of all, so what is the angular momentum formula? See, the velocity vector makes angle theta with the radius vector. So then the angular momentum is calculated by the formula, see, the distance multiplied by the component of the linear momentum in the perpendicular direction. So what is the perpendicular component? So mv is the linear momentum in this direction, and this angle is 90 minus theta, so mv sine theta. So mv sine theta is the perpendicular component of the linear momentum, and also the distance is multiplied. So let me take this point to be P. So the angular momentum at the point P, denoted by LP, is given by mv r sine theta. So this is the angular momentum at that particular point. Now take some specific cases. So this point, so take this point to be Q. So the right hand point, at that point what is the angular momentum? Let me take the speed to be say V1 and this distance R1. So what is the angular momentum at that point? So LQ equals, so M V1 R1, and that's it, because the angle here is 90 degree. So M V1 R1. So that is the angular momentum at the right hand point. Similarly, let us calculate the angular momentum at the left hand point. So take it as R, and the speed can be taken as V2. So the angular momentum at that point, LR, is given by, so same formula, M V2 R2, this distance R2. So all these values are equal as per this rule. So LP here is equal to LQ, that is equal to LR. Not only these points, at any point you find the angular momentum, all those values are same. So that is the conservation of angular momentum. As a particular case, let us take the angular momentum at the right hand point, that is mv1 r1, that is equal to this end point mv2 r2. So this gives you the relation. So v1 divided by v2 is equal to r2 divided by r1. See, R2 here is the minimum distance. So that means V1 is the minimum speed. So the ratio of the velocity, so that is inversely proportional to the ratio of the distance. So that means the minimum speed on the orbit is at the right hand point. Okay, when the distance is more, the speed will be minimum. So the minimum speed, is V1. So V1 here is the minimum speed. Similarly, the maximum speed, so maximum V is V2, so the left hand point. So at the closest point, the speed will be maximum, and at the farthest point, the speed will be minimum. So this is one important idea, but we'll talk about this in detail in the later part of the topic. But here, so angular momentum at any point is a constant value, and also particularly the speed at the right hand point, the farthest point, is the minimum speed, and at the closest point, the speed will be the maximum. So that's about the conservation of angular momentum. Alright, so next we'll talk about the conservation of energy. When an object is revolving around another object in an elliptical orbit, the gravitational force, which is a conservative force, is the only force acting on this object. The total energy is always conserved, which means you find the total energy at any point on the orbit, so that will have a constant value. So let us consider this object at a distance r with the speed v. So let us calculate the kinetic energy. So what is the kinetic energy at that point? So the speed is v, so half mv square. So this we know already. So when the speed is known, so the kinetic energy can be calculated. So similarly, the potential energy. So what is the potential energy at that point? So the potential energy at a distance r is given by this formula. So minus gmm divided by r. So you're familiar with all this formula already. Now the total energy. So this we need to remember as a formula. So minus gmm divided by 2a. So this is the total energy. So where 2a is the length of the major axis. So this is the total energy in an elliptical orbit. So we don't derive or anything, we just remember this as a formula. So the kinetic energy plus potential energy is the total energy, but that total energy is always a constant. But these two values, unlike circular orbit, they are not constant values. In circular orbit, the speed is always constant, and similarly the distance r is also constant. So here the potential energy and kinetic energy both are variable values, but if you add these two, we'll get the total energy, which is always a constant value. So the conservation of energy along with the conservation of angular momentum is an important concept for solving many questions in this topic. So be thorough with all these concepts. Alright, so here we'll talk about Kepler's laws. You know, before Kepler arrived in the scene, people believed that all the planets revolved around the sun in a perfect circular orbit. Before Galileo's time, people even believed that the sun was moving around the planet Earth, not the other way around. So this geocentric model, or rather the egocentric model, that the whole universe is centered at me, all celestial bodies are revolving around me. So this idea was later trashed by many scientists like Copernicus and Galileo among others. So science has since come a long way. Anyway, back to Kepler. So let's invite Kepler in our discussion.
So, you want me to believe this is Kepler?
Okay, if not Kepler, at least believe that this is Kepler's apparition. What matters is his laws, not the dude. So Kepler's first law, also called the law of orbit, is given by
all the planets revolve around the Sun in elliptical orbits with the Sun at one of the foci.
So all the planets revolve around the Sun in elliptical orbits. Alright, even if it is circular for some planets, we will still consider that to be a particular case of ellipse only. So the orbit of any planet is elliptical in shape. See, there are certain terms you should be familiar with here. So like the farthest point on the orbit from the Sun is called by the name aphelion. Sometimes we refer to the distance as aphelion. Similarly, the closest point is called perihelion. So aphelion is the farthest point, perihelion is the closest point. So if you consider an object like the moon revolving around the planet Earth, the same terms are referred to as apogee and perigee. So apogee or aphelion, farthest point, perigee or perihelion, the closest point. So we know the distance apogee, right? We have seen in ellipse from the focus to the end of the major axis, the farthest end of the major axis, that distance is a plus AE. So that means the apogee or aphelion distance is a plus AE. Similarly, the perigee or perihelion distance is a minus AE. So this you should remember as a formula. Alright. So these are certain things you should know about Kepler's first law. So Kepler's first law gives you an idea of the shape of the orbit of the planet. And the next one is Kepler's second law, which is called the law of area. So that is given by, so where is our beloved Kepler?
The line segment joining the Sun to the planet sweeps equal areas in equal intervals of time.
So the radius vector which joins the Sun to the planet sweeps equal area in equal interval of time. That means the rate at which that area increases is a constant. That's what Kepler's second law is. So let us prove Kepler's second law. Alright, so let us consider a small time interval dt. In that time interval, the area covered is dA. So let us find that area dA. So it looks like a triangular region, right? For very small interval of time dt, so it will be approximately considered a triangular region. So that curved portion ds is treated like a straight line path for very small values. So let us find the area of the triangular region. So how to find the area? So we'll use this formula. So for a triangle with two sides a and b, and the angle between them is also known theta. So what is the area of the triangle? So this area is half AB sin theta. Alright, so this is one formula for area of triangle. So if you don't want to use this formula, so we'll have to drop a perpendicular here. So that is the height of the triangle. Alright, so you can find this height using the basic trigonometric idea. So in this right angle triangle, you can use sin theta. You'll get the height. So once height is known, half base height, that will also give you the area of the triangle. But let me use this formula. So what is the area of the triangle? So dA is equal to half r that side ds multiplied by sin theta. Alright, now you divide this expression by dt because we need the rate of change of that area. So divide this by dt. So this gives you the value half r ds by dt multiplied by sin theta. Okay, so what is this ds by dt? So that is the speed of the object, right? So ds by dt is the rate at which that distance, right, increases. So that means ds by dt is the speed. So half r v sin theta. Alright, so now what you do in this expression, so you multiply and divide by m in the numerator and denominator, r v sin theta. So if you observe, so this numerator is the expression for the angular momentum. Alright, so mvr sin theta. So that is the formula for angular momentum. So that is equal to angular momentum divided by 2m. So that is dA divided by dt. So the rate at which the area increases is a constant. Okay, dA by dt is a constant because the angular momentum is constant at any point on the orbit. So this value is a constant. So that is the proof of Kepler's second law, right? dA by dt is constant. So that's what we have proved it. So this whole expression is a constant. Okay, so that is the proof of Kepler's second law. But we'll do a little further right here. So we write it as dA equals L divided by 2m multiplied by dt. Alright, so let's do the integration both the sides. So we do the integration over the entire length of the curve. Alright, so that means this is the total area enclosed by the curve, right? So that value is pi ab, right? As we know, the area of ellipse is pi ab, the total area. this is equal to L divided by 2m multiplied by dt. So this is the total time to complete that orbit. So that is the time period, so t. Alright, so this gives you some relation. So L is equal to 2 pi a b m divided by that time period. So this is one formula. You can use it if required in the question. The relation between the angular momentum and the time period. Alright, so there is a relation between these two. So that can also be used whenever required. So that is Kepler's second law. The rate at which the area is swept by the radius vector is a constant value. Okay. So the next one is Kepler's third law, which is also called the law of period. So that is given by
the square of the time period of revolution of a planet around the Sun is directly proportional to the cube of the semi-major axis of its elliptical path.
So you can easily relate it with the time period in a circular orbit, right? So there we had the square of the time period is proportional to the cube of the orbital radius. So r there is replaced here with the semi-major axis a. Okay, so we've also written one more formula. So t, the time period, is equal to 2 pi divided by root gm multiplied by a to the power 3 by 2. So there we had written r to the power 3 by 2. So these formulae are similar to the circular orbit. Okay, but if you observe this formula, so the time period depends only on the length of the major axis a, not on the minor axis, which means if you reduce the length of the minor axis, the orbital period does not change. So all these shapes have the same orbital period. So generally, so the farther the planet is, longer the time taken by it to complete the orbit. For example, the farthest planet Neptune takes about 600 times more time compared to the closest planet Mercury. Now that we're done with all the concepts required for solving questions of this topic, so here is a list of all concepts that we can refer to. The apogee and the perigee of the moon's orbit around Earth are in the ratio 10:9 and its minimum speed is 3510 km per hour. If v is the maximum speed and e is the eccentricity of the elliptical path, then alright, so here in this question there is something given about the moon's orbit around the planet Earth, the apogee and the perigee. So that means the farthest point and the closest point are at distances in the ratio 10:9, and also the minimum speed of moon is given. We need to find its maximum speed. So we know that the object moves the slowest at the farthest point and vice versa. So what we use here is the concept of conservation of angular momentum. So you find the angular momentum at the right end point and equate it to the one at the left end point. So we get the answer straight away. So we'll use the concept of angular momentum here. So what is the angular momentum at the right end point? See, these points, finding angular momentum at these points is relatively easier compared to the other points, as the velocity vector here is perpendicular to the radius vector. So the angular momentum is simply the linear momentum multiplied by the distance. So which means mv1. So that is the linear momentum multiplied by the distance r1. That must be equal to the angular momentum at the other end point. So mv2 r2. So what is asked in the question is v2. So v2 equals, so v1 multiplied by r1 by r2. So these values are given in the question. So v1 is given 3510 multiplied by, this ratio is given 10/9. That's all. If you just do the calculation here, so this is 3, it will 9, 0, 0. So 3900 km per hour. So this is the speed at which our moon is orbiting our planet Earth.
So, moon is faster than the fastest jet aircraft? What's the speed of Earth then?
We'll find that too, but before that let's complete this question. So it is also required in the question to find the value of the eccentricity of the elliptical path. So let us use this ratio here. So r1 divided by r2 equals, so this r1, that is the apogee, so that has a formula, r from the simple geometry of the ellipse. So from the focus to the right end point, so that is the distance apogee. But from the center to the end point, so the distance is a, so half of the major axis, and from the center to the focus, the distance is AE. So this you're supposed to remember. So this total distance, A plus AE, is what our length of apogee is. So R1 is A plus AE. Similarly, we can find R2. So R2 is this perigee distance, that is this distance A minus AE. So R2 can also be found A minus AE. So this ratio is given in the question 10/9, and that must be equal to, so this value 1 plus E divided by 1 minus E. So just do the multiplication, equals 9 plus 9E. So this is the answer. So the eccentricity is 1 divided by 19. So this is the eccentricity of the elliptical path, and this is the maximum speed of moon, and that is the answer to the question. The aphelion and the perihelion of Earth's orbit around the Sun are 1.52 times 10 to the power 8 kilometer and 1.48 times 10 to the power 8 kilometer respectively. The speed of Earth when it is at a distance from the Sun equal to the semi-major axis is. So here the aphelion and perihelion distances of Earth's orbit around the Sun are given. Using that, we need to find the speed of Earth at a particular distance from the Sun. Now here in the context of Earth moving around the Sun, the terms aphelion and perihelion are used instead of apogee and perigee, but technically they mean the same, and we are just going to use the same concept here. So we need to find the speed of Earth at a distance equal to the semi-major axis, so half of the length of major axis. So let us first find the length of the major axis. So from the simple geometry of ellipse, so from the focus to the end point, that distance is what we call aphelion, r1. Similarly, other end point, r2. So this total distance is the length of the major axis, 2a. So required length 2a equals r1 plus r2. So this r1, that is the aphelion distance, so that is given in the question, 1.52 multiplied by 10 to the power 8. Similarly, r2 is given 1.48. Now if you add these two values, we get the answer 3 multiplied by 10 to the power 8. So this is the distance 2a, but what we need is half of the length a. So a equals 3 by 2 times 10 to the power 8 kilometer, that is the speed. Let's convert this into meter, which is our standard unit for doing calculation. So this equals, so 3 by 2 multiplied by 10 to the power 11, right? Multiplying this by 10 to the power 3. So meter. So this is the required length of semi-major axis. We can keep it for later reference. Alright, so here we need to find the speed of Earth at a particular distance from the Sun. Now, unlike the last question, we don't use the concept of angular momentum here, as the angle between the radius vector and the velocity vector is an unknown value here. So instead we use the concept of energy. So we know that the total energy at any point on the orbit is a constant value. So you find the kinetic energy at that point. So added to the potential energy, so that will give you the total energy, which is a constant value. So what is the kinetic energy formula? So that is simply half mv square. So v is taken as the speed of Earth at that particular point. Similarly, find the potential energy. So minus g m divided by r, the distance, but that distance is given in the question, a, and that must be equal to the total energy minus g m divided by 2a. So this value is a constant at any point on the orbit. So this is a constant value. So this sum is always a constant. So let us now do the calculation here. So divide by m. So v squared divided by 2 equals, so if you just add these two values, so we get gm divided by 2a. So this gives you the required value of v, square root of gm divided by a. So this is the speed at which our Earth is orbiting the Sun at that particular point. But unfortunately the options are given in terms of numerical values, so we'll have to go through the tedious process of substituting the value of g, m and a. So do you remember the value of g? 6.67 times 10 to the power minus 11, but I told you to use this value for easier calculations, right? So g value is what, 20 divided by 3 multiplied by 10 to the power minus 11. So this value is approximately 6.67, so this makes the calculation easier. Multiplied by m value is given in the question, 2 times 10 to the power 30 divided by the value of a we found here, 3 by 2 multiplied by 10 to the power 11. So let's do the calculation. So that equals, so 20 times 2 multiplied by 2, that is 80, divided by 9 multiplied by 10 to the power 30, here 22, 30 minus 22, that is 10 to the power 8. So this will give you the value. 80 can be written as 16 multiplied by 5, so that can be written as 4 root 5 divided by 3 times 10 to the power 4. Okay, now this root 5 value is approximately 2.236 something, but this value is given in the question. From that expression, we can write the value of root 5 approximately that value. So that equals 4 multiplied by 2.25 divided by 3 times 10 to the power 4. Okay, so 4 times 2.25, so that is 8 plus 1, 9. So 9 by 3. So this is 3 times 10 to the power 4, or we can say 30,000. Yes, so 30,000 meter per second. So this is our required speed. So but let's convert this into kilometer per hour. So 30,000 multiplied by 18 by 5 kilometer per hour. So this gives you the answer 6 times. So 6 times 18 or 12 times 9. So this is 108,000 kilometer per hour. So this is our required speed. So that is the speed at which our Earth is orbiting around the Sun at that particular distance.
That means right now we are traveling at a speed of 108,000 km per hour?
No, not exactly. So this is the speed of Earth with respect to the Sun. But the Sun or the solar system itself is moving around the center of the Milky Way galaxy at a speed of close to 800,000 km per hour. And the Milky Way galaxy is also moving at a speed of 2 million or 20 lakh km per hour. So that means at what speed are we moving exactly is beyond my calculation limits. Jupiter's moons Ursa and Europa orbit the planet with semi-major axis 1.1 times 10 to the power 7 km and 6.7 times 10 to the power 5 km respectively. If Ursa takes 252 Earth days to complete the orbit, then the time taken by Europa is approximately. Unlike our planet Earth, Jupiter has a lot of moons, about 70 or 80. Two of them are given in the question, Ursa and Europa. The lengths of the major axis of their elliptical orbits are given. Using that, we need to find the relation between their time period. So it is very simple question, direct application of Kepler's third law. So let's use the concept of period here. So we know that the square of the time period is proportional to the cube of the semi-major axis. So that means the ratio t1 square divided by t2 square, that must be equal to a1 cube divided by a2 cube. So a1 is the length of the semi-major axis of the first moon, similarly the second one. So let me take this numerator for Europa and denominator for Ursa. Now that means T1 is given, T1 is to be found, so T1 square, and T2 is given in the question 252 square. So that must be equal to, this A1 is 6.7 times 10 to the power 5 divided by, this is 1.1 multiplied by 10 to the power 7 cube. Okay, so let me do some approximate calculations here. So 6.7 divided by 1.1. So this is approximately 6 divided by 100 cube. Take the approximate value 1 by 16 cube. So this is the value of T1 squared divided by 252 squared. So if you take the square root, so T1 equals 252 multiplied by, the square root of 16 is 4 cube, that is 64. So 1 by 64. So this value is approximately 4. So 4 days. So this is the number of days the moon Europa takes to complete one orbit around the planet Jupiter. Whereas our moon takes about 28 days to complete the orbit around the planet Earth.
But our moon is closer to the planet Earth than Europa is to the planet Jupiter. Still, Europa takes much less time. How?
See, that is true. Our moon is close to 400,000 km from the planet Earth, whereas Europa is more than 600,000 km from the planet Jupiter. But still it takes very less time compared to our moon. That is because, so this ratio works only for one particular system. If you want to compare two different planets, so we have to use the direct formula. So what is the formula for the time period, which is 2 pi divided by root gm multiplied by a to the power 3 by 2. So this time period also depends on the mass of the planet. So Jupiter is several times heavier than the planet Earth, so that makes the denominator so much bigger. So that is why the time period is very less, just 4 days compared to the moon of the planet Earth. If Earth stopped orbiting the Sun suddenly, the number of days it would take to crash into the Sun is. So why would Earth stop orbiting the Sun? So hypothetically, suppose there is a mysterious force that stopped the motion of the planet. In that case, what would happen? See, first of all, the planet would start moving towards the Sun in a straight line path due to Sun's gravitational attraction, and now the planet's days are numbered. So how many days exactly? That's what we're going to calculate here. Alright. Now, see, there are two situations given in the question. The first, it moves in a circular orbit, so that's a normal situation. Actually, it is an elliptical orbit, but we can approximately consider this to be a circular orbit as the eccentricity of this ellipse is very close to 0, so it is almost like a circle. So in the second case, it is moving in a straight line path. So we are going to take this straight line to be an ellipse with the length of minor axis 0. So if you make the length of minor axis 0, so the ellipse will become a straight line. So we will consider that straight line to be an ellipse with the minor axis close to 0. So it is something like this.
But why does the major axis also decrease in length?
See, when the minor axis decreases, the focus is moving towards one end of the major axis. Okay, here the focus is the sun. The sun doesn't move anywhere, right? So sun is fixed at one place. So to compensate that, the major axis decreases along with the length of the minor axis. So that the sun will be at one end of the major axis. Is that okay? Now the distance between the sun and the planet is the total length of the major axis. Is that okay? Right. Now what we use here is the concept of the same period, right? Alright, so there are two situations here. In the first case, it is a circular orbit. See, for the circular orbit with radius r, what is the time period? So this is the formula for the time period. So the square of the time period is proportional to the cube of the radius, right? So this is the time period formula for the circular orbit. Now similarly, the second one is considered to be an elliptical orbit. So elliptical orbit with the length of minor axis almost 0. So here the square of the time period is proportional to the semi-major axis cubed. Alright, so there are two situations here. So here in this case I'll take this as T1, this is T2. So two different time periods. Alright, so here the length of the minor axis, this is length of the major axis. So semi-major axis here, and this is the radius of the circle. Now here, but there is a relation between this r and a. See, in the first case, the distance between the sun and the planet is the radius r. But in the second case, the distance between the sun and the planet is the total major axis of the ellipse. So 2a. So 2a must be equal to, so here what happens? This 2a, the total length of the major axis, so that is same as the radius r. Alright, so this is the relation between this a and r. You substitute in one of the equations. So let me substitute here this r value here in the first equation. So that gives you, so T1 squared is proportional to, so 2a to the power 3. Alright, now let us solve this equation. Let's divide these two equations. Okay, so the ratio proportional, which means ratio must be equal. So T2 squared divided by T1 squared, so that must be equal to this ratio, a cube. Here also a cube, that gets cancelled. So 1 divided by 2 cube. Okay, alright, so now that gives you our required answer. T2 squared T2 is equal to T1 divided by square root of 2 cube, which is 8. The square root of 8 can be written as 2 root 2. Okay, now what is this T1? So T1 is the normal time period of the planet Earth, right? So that is in the first case, so circular orbit. So that T1 is our 365-day period. So this is 365. So divided by 2 root 2. So if you do the calculation, you will get the answer. But if you want to do the calculation manually, so let me take some approximate values. So 365, instead of 365, you take approximately 364 divided by 2 root 2. So that is, so 364 is 4 times 91 divided by 2 root 2. So that value is, so 91 multiplied by 2 divided by root 2. So that is root 2. So 91 multiplied by square root of 2. So this calculation can be done easily, approximately 91 multiplied by 1.4, right? So this will give you an approximate value, which is 128. Right, so 128 is the value of T2, but that is not the answer to the question. So this is the time period in the second case, the time period to complete this elliptical path, but this is a one-way path. Remember, once it reaches the sun, there is no return journey. So it is just a one-way journey. So our required answer is not 128, but just half of this value. So our required answer is 128 divided by 2. So that is 64 approximately, right? So the closest answer here is 64.5. So that is the answer to the question. So our planet Earth would take about 64.5 days to reach the sun.
So, all of us will die in 64.5 days.
See, no, much before that. You know how many forces are working on us to keep us alive on this planet? Even for small disturbances, we are gone. First of all, when the planet stops suddenly, all the loose objects on the planet will fly away, including all the living, non-living things, trees, topsoil, ocean water, everything will fly away. Where is the chance of survival, even for a minute? Even the planet will not survive for these many days. As it gets closer and closer to the sun, the gravitational pull is so strong that the planet will be ripped apart even before it reaches the sun. So this 64.5 days is kind of a fancy answer, and in reality we never know. The apogee and the perigee of the planet's orbit given in the figure are in the ratio 11:3. The ratio of time taken by the planet to reach from the point A to B in the clockwise and anti-clockwise direction is. So here the planet is at the topmost point. That means one end of the minor axis. It has to get to the other end, either in the clockwise direction or in the counterclockwise direction. But in both the cases, it has to cover the same distance. So it will take the same amount of time. So that means the answer must be 1:1, right?
But the clockwise path is farther from the sun, so it will take more time.
Yes, that means we have to use the concept of Kepler's second law, or the law of area. Alright, so as per the rule, the rate of change of area is a constant. So dA divided by dt is a constant. Alright, so the rate at which the area is swept by that line segment is a constant value. So dA by dt is a constant. On integration, this gives you A equals Ct. Alright, so the area is proportional to the time taken. So the ratio of the time taken in the two cases, T1 divided by T2 is equal to A1 divided by A2. So our required ratio of the time taken is same as the ratio of the two areas marked in two different colors. Alright, so let us find that area. So more of a math question now. See, let's find this area from the ellipse. So this is the minor axis. Alright, now so you take this part. So that part has area. So half of the total area of the ellipse, which is pi AB, right? So this portion has area pi AB. Now the area A1 includes this portion also. Alright, so this is a triangular region. So to find the area of the triangle, we use the basic formula half base height. So this is the base of the triangle, which is the length of the minor axis, and this is the height. So that is the distance from the center to the focus. So that distance is AE. So that means the area of this portion is half of base is 2b multiplied by the height of the triangle, which is AE. So we found the area of this part and area of this part. This total gives you our required area A1. So let us substitute this value there. So this value is pi AB divided by 2. Alright, plus similarly the other area, which is 2ABE divided by 2. So the whole thing divided by A2. A2 is the area of this portion. Alright, so that is done similarly. So this total area, this is half of pi AB and minus this area of the triangle. Okay, if you subtract this portion, we'll get only this part. So that is pi AB by 2 minus 2ABE divided by 2. So this gives you the answer. We can remove all the common factors here. So divide by, so AB, okay, by 2. So this gives you the value pi plus 2b 2e divided by pi minus 2e. So this is the value of the ratio of the time period. So that is the answer to the question, but we have to find the value. This is the eccentricity of the ellipse, so you have to find that value, and we know the value of pi, right? Approximately 3.14, or we can take 22 by 7. So let us find the eccentricity. We have already done a similar question. If you remember, to find the eccentricity, we use the ratio of the apogee and the perigee. Okay, R1 is to R2. So that is A plus AE divided by A minus AE, right? So this is the length of apogee, if you remember, and then this ratio is given in the question. So 11:3. So 11 by 3 is equal to 1 plus E divided by 1 minus E. So that gives you the value of E. So if you do all the multiplication here, so that will give you the answer. Alright, so 4 by 7. So this is the value of the eccentricity. So that value we can substitute here to get our required ratio of the time taken. Alright, so T1 by T2 is equal to pi. So pi I am taking approximately 22 by 7, right? Plus 2e. 2e is 8 by 7 here, divided by 22 by 7 minus 8 by 7. So this gives you our required answer, 22 plus 8, 30 divided by 14. So that is 15 divided by 7. So that's it. So that is the answer to the question. We need that ratio of the time taken, and that is equal to 15:7. So that must be the answer to the question. From a satellite orbiting Earth with orbital radius 3 times the radius of Earth r, an object is ejected so that the satellite speed is reduced to half. The closest distance of the satellite from the center of Earth is. See, as long as the satellite is moving with the orbital speed, it will stay in the circular orbit, but once the speed is reduced, it will start moving in an elliptical orbit. So here what happens, so some object is ejected from the satellite, and due to momentum conservation, the speed of this satellite is reduced. So with the reduced speed, it will start moving in an elliptical orbit. So the distance of the satellite from the center of the earth does not remain constant. So it gets little closer at the lowermost point, and that distance is what we need to find. So what we use here is the concept of conservation of angular momentum. So angular momentum. So let us find the angular momentum at the two endpoints. So what is the angular momentum at the topmost point? So mass times the velocity, which is the half of the orbital velocity, multiplied by the distance, which is 3r, and that must be equal to the angular momentum at the lowermost point, so which is m. So that speed is taken as v and distance is r. Some relation we get, so which is 3r VO, so that must be equal to 2vr. Okay, so this is some relation, so we can use it for our calculation. Now we'll also use the conservation of energy. So we find the energy of these two endpoints and we can equate them. So what is the energy at the topmost point? So the kinetic energy, half m v squared. So v here is, so VO by 2 the whole square, which means, so this is the kinetic energy, and the potential energy is minus gmm divided by the distance, which is 3r, and that must be equal to kinetic energy half mv squared at the lower end minus gmm divided by r. So now we have to simplify this expression. So we can group these two terms together. So dividing by m, so gm multiplied by 1 by r minus 1 by 3r, and that is equal to, so this value, so half this v squared. So we can substitute this value from this, so that gives you 9r square VO squared divided by 4r squared minus this this value, so VO squared divided by 4. So this gives you the answer. So we can take out the common factor. We can even take this 9r square, the VO squared, and then divided by 8, and that is equal to 1 by r squared minus 1 by 9r squared. Okay, so that is equal to, so 9r squared by 8. So this is VO squared, so that is the orbital speed at a distance 3r from the center. So what is the formula for orbital speed? Gm divided by 3r, okay, squared. So that equal to, this is of the form a squared minus b squared. So that is 1 by r minus 1 by 3r multiplied by 1 by r plus 1 by 3r. So a squared minus b squared, I'm using a plus b, a minus b, so that is equal to gm multiplied by 1 by r minus 1 by 3r. So now cancel out this term, and this gm gets cancelled. What else? So this r gets cancelled, 1 3 also we can cancel. So what is left? So 8 is equal to, so this is 3r, I'm multiplying this 3r inside here, so 3r divided by r plus 1, that gives you the value of r, which is 7 equals 3r by r, so r equal to 3r divided by 7. So this is our required distance, and that must be the answer to the question, right?
But this value seems to be less than the radius of Earth. How is it possible?
You're brilliant. I thought you wouldn't observe this. So this value of r is less than the radius of the earth. How is it possible? The satellite cannot penetrate through the surface, right? So actually what happens is the satellite crashes onto the surface. That means it just stays on the surface. That means the minimum distance of the satellite from the center of the earth is just the radius of the earth, and that means our required answer is simply the radius of the earth, r. So that is the answer to the question. A satellite is orbiting Earth at an altitude equal to the radius of Earth. If the speed of the satellite is reduced, it crashes onto the surface at an angle 60 degrees. The percentage reduction in its speed is. So just like the last question, here too the satellite is crashing onto the surface with a reduced speed. So that reduced speed is what we need to find. So we are just going to use the same concept of conservation of angular momentum and energy. So let us find the angular momentum at the two endpoints, and then we can equate them. So what is the angular momentum at the topmost point? So mass multiplied by the speed there is taken as v multiplied by the distance. So that is 2r. See, 2r is the distance, not r. R is the altitude from the surface. Now here from the center to the satellite, the distance is 2r. And that must be equal to the angular momentum at the other endpoint. So that is m. So the speed is taken as v1 and the distance is r multiplied by, see this time the satellite is crashing onto the surface at certain angle. So the angle between the radius vector and the velocity vector is not 90 degree here. So that angle here is 30 degree, not even 60 degree. 60 is the angle made with the surface. So the angle between the radius vector and the velocity vector, so that is 30 degree. So mv1 r sine 30. So this is the relation between them. So if you simplify this, r gets cancelled, m. So what we are left with, sine 30 is 1 by 2. So 4v, that is equal to v1. So this is the relation between the two speeds. So v is the reduced speed at the topmost point, v1 is the speed just before the satellite hits the surface. Similarly, let us use the energy conservation here. So what is the kinetic energy at the topmost point? Half m v squared, and the potential energy is minus g m divided by 2r, and that is equal to the energy at the other end point. So half m v1 square minus g m divided by r. So this is the relation. So let us simplify this expression. We can bring these two terms together. So divide by m. So we get gm divided by 2r, and that is equal to, this is half v1 square. That v1 is 4v. So that means 16v squared minus v squared. But what is this gm divided by 2r? See, that is the orbital speed at a distance 2r from the center of the earth, right? See, orbital speed formula is gm divided by r. So at a distance 2r, the orbital distance is root gm divided by r, right? The orbital velocity. So that means this is the orbital velocity squared. Okay, so that is equal to 15 by 2 v squared. So this gives you the relation v is equal to 15 by 2, 7.5. So 1 divided by root 7.5 times the orbital speed. So now we got the relation between the reduced speed and the actual orbital speed. So, but now we need to find the percentage reduction. So we need to find the exact value of this. But as the options are not very close to each other, let us just find the approximate values. So root 7.5 is an unknown value. So let us find an approximate value. So but 7.5 lies between 4 and 9. So I'm writing this as, this is less than root 4 then, but greater than root 9. So because 7.5 lies between 4 and 9, so this relation holds. So this value is known. So 1 by root 7.5 is less than 1 by 2, but greater than 1 by 3. So this value is approximately 0.33. This is 0.5. So the required value lies between 0.33 and 0.5. I'm taking the value approximately somewhere between 0.33 and 0.5, which is 0.4. Let me take. So let us take our required speed v to be 0.4 times our orbital speed. So our required speed is only a fraction of the orbital speed. What fraction? 0.4. So that means what is the percentage reduction? So the percentage reduction in the speed is simply 60%. Okay, 0.4 only. So there is a reduction of 60%. So we can find out the closest option here. A satellite of mass m orbiting Earth with orbital radius 4 times the radius of Earth r suddenly encounters an atmospheric drag kv squared proportional to the square of the speed. The time taken by the satellite to crash into Earth is. So here also the satellite is crashing onto the planet. So many crashes are happening today, but the situation here is different from that of the last question. See, in the last question the speed is reduced suddenly. So instead of circular orbit, it takes an elliptical orbit. But here, due to an external force, the speed is reducing gradually. Right, it decreases continuously, so it still maintains the circular orbit then, but with a reduced radius, the radius is also reducing continuously. So the situation is somewhat like this. So this shape is more like a spiral, right? So which means approximately we can take this to be a circular orbit, but the radius is reducing continuously. So we can take this to be a circular orbit at any point approximately, but the radius does not remain constant, it is reducing continuously. Finally, the radius of the orbit becomes the radius of the planet Earth. That is when it crashes onto the surface. Alright, now what we do is, let us first find the speed of the satellite at the topmost point, that is the initial speed. So what is the initial speed? So taken as v1, so that is equal to the square root of gm divided by 4r. This is the orbital speed at a distance 4r from the center. Similarly, we will find the final speed. So what is the final speed? That is the speed just before it hits the surface. So that's taken as v2. That is the orbital speed at a distance r from the center. So distance is r from the center. So this is the orbital speed. So we have found v1 and v2. Yes.
But in the last question we didn't take the final speed to be the orbital speed.
See, that's what I told you. This question is different from the last question. In the last question, the speed dropped suddenly. So that means instead of circular orbit, it took an elliptical orbit. But here in this question, the speed is reducing continuously. So that means, so it is always considered a circular orbit, but the speed and the radius is reducing very slowly. So at any point on the orbit, we can consider the speed to be the orbital speed at that particular distance. So this is the orbital speed at a distance r from the center of the earth. Is that okay? Alright. Now obviously we can't use the conservation of energy or angular momentum here because there is an external force acting on the object. So what we use here is simply the Newton's laws. We simply use Newton's second law. So what is that? Force equals mass times the acceleration. So the force is given in the question, so that is kV squared. That equals mass times the acceleration is the rate of change of the velocity. So this is the relation. So use simple calculus. So let's do the integration. So this is k by m dt equals dv divided by v squared. So shall we do the integration here? So here dt, so the integration is over t. So t starts from 0 to take the time, the final time to be t. And the speed, the initial speed is taken as v1 and the final speed is v2. So let us do the integration. So this will simply become kt divided by m. And that is equal to, so the integration of this is 1 by v and from v1 to v2. So this will give you the answer 1 by v1 minus 1 by v2. And this v1 and v2 are already found here. So let us substitute these values here. So v1 here is, so gm divided by 4r root. So, but we have to take the reciprocal, so that is 2 root r divided by gm and minus here root r divided by gm. So that gives you the answer, so square root of r divided by gm, and that is the value of kt divided by m. So from this we can find the required time t, but in the options it is not given in terms of capital G, the options are given in terms of small g. It should have been mentioned in the question what this g is, but it is understood, right? So it is the acceleration due to gravity near the surface of the earth. So let us get it in terms of small g. So multiply and divide by r. So this is r square divided by gm 1 by r. So what is the formula for the acceleration due to gravity? So that is gm divided by r square. So this value is simply square root of, this is the reciprocal of that 1 by gr. So that is the value of kt divided by m. So that gives you a required answer t. So m divided by k multiplied by 1 divided by root gr, and that is the answer to the question. A spacecraft carrying a lunar orbiter of 1/3 of the total mass reaches Moon in a parabolic path. During the closest approach, the orbiter is set into a circular orbit around Moon. The percentage increase in the speed of the spacecraft in the process is. So here the spacecraft reaches the Moon in a parabolic path.
But the shortest path is a straight line, then why does it travel in a parabolic path?
You mean something like this? It doesn't work like that. First of all, to leave like this in a straight line path, it requires huge amount of energy. Secondly, the landing cannot happen like this for obvious reasons. So the actual situation may be something like this. To reduce the energy consumption, first of all, the spacecraft moves around the planet before it starts heading for Moon. And there it gets separated into two parts. One part is orbiting the Moon, the other one is moving away. See, the actual situation may not be like that given in the question, but for the sake of this question we can consider this situation. So it's like this. So this is the Moon and our spacecraft is reaching the closest point on the Moon with the speed, let's take the speed to be v1, and the mass of the spacecraft is m. Okay, but when it reaches this point, it gets separated into two parts. So one is moving with the velocity v2, and so this is moving in a circular orbit. So the other part is moving away with the speed v3. So this mass is also given 1/3 of the mass, that is m by 3, and the remaining 2m by 3. Alright, now what we are going to use here is the concept of conservation of momentum. See, the only force here is the gravitational force. So that is acting in a perpendicular direction. So there is no component of this gravitational force in the horizontal direction. So the momentum just before this separation, so you find the momentum, and after separation you find the momentum and equate them, you get the answer. So what we use here is the concept of the momentum. So shall we find the momentum before reaching that point? So that is the mass multiplied by the speed, mv1. Similarly, the total momentum after this separation. So the momentum of this object is m by 3 multiplied by v2 plus the other part 2m by 3 v3. Okay, so if you simplify, so we'll get v1 equals 3v1 equals v2 plus 2v3. So we got a relation between the speeds of all the three objects. Now let us simplify this. So what is this v1? v1 is the speed, the initial speed, but this object moves in a parabolic path. But we have seen that the parabolic path corresponds to the escape velocity. So when an object is moving with the escape velocity, so that path is the parabolic path. So that means v1 here is the escape velocity. So 3ve. And v2. So this object is moving in a circular orbit. For a circular orbit, the speed must be the orbital speed. So what is the orbital speed? So let's take VO and plus 2 v3, and v3 is what we need to find. Alright, so now this escape velocity and the orbital velocity, so they have a relation. So the escape velocity is root 2 times the orbital velocity. So this orbital velocity can be written as the escape velocity divided by root 2 plus 2v3. So let us simplify this. So what we need is the value of v3. So v3 here is 3 root 2 minus 1 divided by 2 root 2, so multiplied by ve. Alright, so let us simplify this. So this value is equal to, so this is 3 by 2, so 1.5 minus 1 by 2 root 2 multiply and divide by root 2, so it will become root 2 divided by, so 4 times ve. So this escape velocity, that is the initial velocity v1, so v3. So we got the relation between v3 and v1. Let's simplify this further. So this value is 1.5 minus, so root 2 value is approximately 1.4 divided by 4, so that will be approximately 0.35 times v1. So our required v3 is equal to, so 1.15 multiplied by v1. So the final speed v3 is little more than our initial speed v1. So how much more? 0.15 times. That means there is an increase in speed, right? So there is a 15% increase in its speed, and so that is the answer to the question. So we are done with the chapter gravitation, so you can keep this list of formulae for reference.